suppose that we had the span of the following vectors: 1, 2, 3, 2, and 1, 1. The question is, are these linearly dependent or independent? Meaning, can I take one vector and represent that one vector as a linear combination of the other two vectors? That is, can I find two numbers, multiply them by the other two vectors, add them up to get me the third vector? So let's try to see if we can address this, right? We have here 1, 2. And suppose I'm curious, can I write 1, 2 as a linear combination of 3, 2 and 1, 1? Recall, this is the same as saying 3, 2, 1, 1 multiplied by the vector alpha 1, alpha 2. And from this, I can create what's called an augmented matrix. Okay, now here's the idea. I want to reduce this matrix down. If I am able to reduce this matrix down such that this is the identity matrix, then that means that the three vectors are linearly dependent. If I can't reduce this down, it means that the three vectors are linearly independent. So let's observe. I'm going to just keep the same screen, but for the sake of efficiency, move all of this here. Okay. Now, let's apply our Gauss-Jordan elimination. Remember, we want to convert this to 1. We do that by dividing the whole row by 3. And we're left with 2, 1, 2. I want to get rid of this 2. I do that by multiplying this row by minus 2, right? Minus 2 times 1 is minus 2, plus 2 is 0. So I do that. Minus 2 times 1, first of all, this stays the same. Minus 2 times 1 is minus 2, plus 2 is 0. Minus 2, okay, this is 1 minus 2/3. And then this is 2 minus 2/3. Okay, now if you simplify that down, that's the same as 3/3 minus 2/3, which is just 1/3. If you simplify that down, that's the same thing as 6/3 minus 2/3, which is 4/3. Okay, now we need to convert this to 1. We do that by multiplying the whole thing by 3. So looking down on our next step, leave that as 1/3. Leave that as 1/3. Multiply the whole thing by 3. We get 0, 1, and 4. Okay, so now, how do I get rid of this? Well, minus 1/3, right? Multiply the bottom row by minus 1/3, and then apply it to this. Anything times 0 is 0, plus 1. It's something, it's just a something, so that just stays the same. And by the way, this bottom row stays the same. Here we have minus 1/3 plus times 1 plus 1/3, which is 0. Then we have minus 1/3 plus 1/3, so that's 1/3 minus 4/3. And here we get minus 3/3, which is minus 1. And here we get 4. Because we get the identity matrix here, what we end up having is one vector being represented in terms of the other vectors. How so? Well, by doing that set of manipulations, we initially started with AX equals B, where this is our B, this is our A. And remember, we were trying to basically say, can we write the vector 1, 2 as a linear combination of 3, 2 and 1, 1, right? That was the same thing as the 3, 2, 1, 1, and then alpha 1, alpha 2. But what we basically just did was reduce the matrix down. Where now on this side, we have 1, 0, 0, 1. And on the right-hand side, we have -1 and 4. That's what we did. That's what the row operations of the matrix do, is it reduces it down. But notice when you multiply this out, right, matrix multiplication, alpha 1 times 1 is alpha 1 plus 0 times alpha 2. So this says that alpha 1 is equal to -1. 0 times alpha 1 is 0 plus 1 times alpha 2 is just alpha 2 is equal to 4. So what does this tell us? This says that I can rewrite the third vector as follows. -1 times that plus 4 times that. Let's see if that's true. 4 minus 3 is 1. 4 minus 2 is 2. And we get that result. So you see what we did? We worked backwards to be able to find those two numbers. And because we were able to find those two numbers, that means the 3 vectors, therefore, are linearly dependent. So what have we concluded here? We have concluded that, let's suppose I removed this augmentation. Pardon. If I take any set of vectors and I form a matrix with it, and I do matrix operations on it, if I don't get something that looks like unique vectors, that is, if I'm not able to reduce this down to something that looks like an identity matrix or close to it, but I have another column in here, that allows that can be written as in terms of the other two, then I have the vectors linearly dependent. Now, interestingly enough, if I just form the matrix of vectors, any set of given vectors, and I can correspond them, okay, assuming I don't switch rows, that's the important, or columns. If I don't switch rows and columns, and I go through the whole set of operations, then the columns that correspond to these guys here, the 1, 0, 0, 1s, and more generally 0, 0, 1s, 1, 0, 0s, etc., the collection of those vectors corresponding here are the set of linearly independent. So notice that this didn't boil down to a 0, 1, or 1, 0. But these do. So this first column reduced down to this, the second column reduced down to that. Because that happened, those columns are the linearly independent ones. So let's take another 3 vectors. Okay, the question is, are these linearly independent? We can make that determination by forming a matrix of the vectors and applying the Gauss-Jordan elimination algorithm on it. Notice the 1 is here, life's good, multiply -1 and apply to this row. -1 times 1 plus 1 is 0. -1 times 3 plus 2 is -1. -1 times 2 plus 1 is -1. Notice, I'm going to shorten this up a bit. We're going to do the same thing, but for this row, -1, 1 is 0, -3, and 1 is -2, -2, and 0 is just -2. And I left the first one here. So I converted the whole column to zeros. The next is this here. I need to convert that to 1. We do that by dividing the whole row, or multiplying the whole row by -1. Doing that leaves us with this matrix here. Now I use this as a pivot to get rid of the 3 and the 2. First, I get rid of first I'm going to write the middle row because that doesn't change. Pivot row never changes until the next step, in which case we have a different pivot row and that doesn't change, right? So here I want to get rid of the 3. I notice I have the 1, multiply this row by -3 and apply. -3 times 0 plus 1 is 1. -3 plus times 1 is plus 3 is 0. -3 plus 2 is -1. Now do the same thing for the 2. How do I get rid of -2? I multiply this whole row by +2. 0 times +2 plus 0 is just 0. 0 times 1, I'm sorry, +2 times 1 is 2, -2 is 0. 2 times 1 plus -2 is again 0. Now you'll notice that I don't have a 1 here, and that's fairly problematic. Okay, what does this tell us? This tells us that I'm not able to get this column to look like this, basically. In order for it to be linearly independent, for these to be linearly independent, I need these to reduce down to the vector 0, 0, 1, uniquely, might I add, 1, 1, 0, 0, and 0, 1, 0. Okay, that's basically what I need them to reduce down to. Now I got 2 of them too. I got those to reduce down, but the third one, you'll notice that didn't reduce down, and that's a problem. What this says is that these vectors are linearly dependent because I can write the third vector in terms of the prior 2 that's over here. What are the quantities for that? If you were to put a bar here, okay, and if this were alpha 1, alpha 2, you can very clearly see that when I multiply this times alpha 1, alpha 2, I'm going to get alpha 1 is equal to -1, alpha 2 is equal to +1. So here I have, if I were to do -1 times 1, 0, 0, plus 1 times 0, 1, 0, what do I get? I get -1 times 1 plus 0 is -1, times 0 plus 1 is just 1, 0 and 0, 0. So they're dependent. Okay, I was able to find 2 constants. That's a problem. Now, which ones are independent? These 2, because I was able to reduce them down to these. You can further prove that, by the way, that these are independent if you need any validation. How do you prove that? Okay, let's see. 1, 1, 1, 3, 2, 1. 1, 1, 1, 3, 2, 1. Okay, the question is, can I find in this case, same deal, I put it in terms of a matrix, an augmented matrix, but it's shortened down now. Notice what's very strange here is that I only have one column, but that's okay. So multiply, we already have a 1 here in the pivot. To get rid of this, we just multiply and apply, right? We get minus 1, 0, minus 1, minus 1. Same deal, minus 1, 0, minus 1, minus 2. And we get 1 with the 3 over here. But what does this say? In effect, this says that minus, if we were to have this as a k, let's say, this says that if I were to multiply this by k, let's see here, hold on. I have 1, 0, 0, and I therefore need alpha, no, just alpha 1. That was alpha 1. What does this say? Alpha 1. Multiplying the alpha 1, I get alpha 1 is equal to 3. Okay, but we can very clearly see, is it alpha 1, alpha 2, alpha 3? Here I have, well, here's the point, okay? In order for me to write, even though I did the Gauss-Jordan elimination here, in order for me to write that in terms of that, I need the following. I need k times this needs to be equal to this, okay? And as we've illustrated through our Gauss-Jordan elimination here, all right, rewrite those equations. This is saying k times 1, k needs to equal 3, and k needs to equal 2, and k needs to equal 1, which has a contradiction because 1 and 2 and 3 do not equal each other. So there's no value of k that I can plug in here such that when I multiply it by this vector, I'm going to get this vector. And that tells me that the two are linearly independent. I'm sorry, the two are linearly, independent. All right. I can't write one in terms of the other. So anyway, the theorem is, just to be clear, that whatever columns are corresponding to the columns I have reduced down to these vectors here, those are the ones that are going to be linearly independent. Now, suppose that this was a vector space that we spanned with these vectors. I could take any number of vectors I want. The question, and to span a space, the question is which ones should I use such that the vectors will be linearly independent. We already went through the process of how to do that. We formed the vectors into a matrix, do Gauss-Jordan elimination, go back to the vectors that correspond to these 1, 0, 0, etc. And those are the collection of vectors that are linearly independent, which will span the same exact space as all the vectors. Those set of vectors, which are linearly independent, that happen to span the same space, is what we refer to as a basis of the space. So a basis of a vector space is a collection of vectors that are linearly independent and they span the whole space. Meaning, when we say span, remember, that means I can take linear combinations of those vectors and create new vectors which are in that same space. If I do this, The number of vectors that are in the basis are what is referred to as the dimension of the space, which is something we talked about much earlier. So usually the process here, when we're looking at different vectors, and more specifically in terms of vector spaces, we're always trying to look at what's the basis, because the basis is the collection of vectors that will generate all of the vectors in the set. So I don't look to characterize, I don't usually look to characterize all of the vectors in the space. I try to look for a basis. And once one has a basis for the vector space, they are then able to characterize vectors in the vector space as just simply linear combinations of the basis.